Now? Great. Okay, as you might have guessed, I will be talking about periodic timetable optimization in public transport. Yeah, as said, I'm working in the mobility lab at ZIP. What we are doing is mostly discrete optimization in public transport. And I just want to show you briefly a few projects that we are currently working on. So line planning in Karlsruhe has been a little time ago. That's why it's not on the slide. We're doing things that have to do with public transport companies and railways. So one thing, for example, is the rolling stock rotation planning for the ICE trains in Germany. These are the high-speed trains. And the question is basically, if given the timetable of the trains, how do we actually put physical trains onto the trips? How do you do that in an efficient way? And Deutsche Bahn, so the operator, wants it in such a way that these plans of which vehicle operates which trip repeat after 7 days. And that's why you see this torus shape here, basically. You see these 7 blue regions, which represent days. And in fact, they're the geographic trajectories of the trains moving through Germany. And on this map, you can basically see how each train moves. And the red parts are the nights where only a few trains are actually moving. And yeah, we are computing those. We have a project that is concerned with electric bus scheduling. The difference to ordinary bus scheduling, of course, being that electric buses need time and space for charging. And this is not negligible because charging takes hours and occupies some space. So that's why public transport companies want plans that actually elaborate this to not build too much charging opportunities and so on, because that's also very costly, and to put more electric buses into operation. Another project is about construction site timetabling, actually here in Berlin. So that's for S-Bahn, the local commuter trains here. And the problem is basically when there's construction sites, and there are many throughout the year, what do you actually do? Right? Trains can obviously not run into the construction site, but they need to turn elsewhere. But where do they turn? What changes are necessary for the timetable, and how does this affect vehicle schedules? That's exactly the question we are solving in this project. And what we also have is something related to machine learning, where we actually do predictive maintenance in the sense that we look at health functions of certain components of trains. In this case, it's just specifically the doors. And yeah, I mean, doors tend to break down at some point, but you can measure this by just having sensors or looking very precisely at the data the motors, the engines, the motors give you. And the idea is basically every component in a train needs to be maintained, let's say, once a week, twice a week, or once a month, depending on what it is. But if you know actually the health status of the train, you can arrange the maintenance slot for the train to be earlier if the component is likely to break down, or later, right? And this way you can do more efficient maintenance plans. And this is what we're doing in that project. So this is just a small snapshot of what we do. We also do more. We do things with cargo. We do things with airplanes. We do things with that work on motorways and so on. Yes, I want to talk public transport. If you have never seen that, it looks kind of like this, especially here in the area. And what also might have occurred to you is that public transport is often operated in a periodic way. That means you know that your ICE trains runs once an hour and your tram runs once every 10 minutes. And this repeats after each period. And this creates the need for periodic timetable optimization. And yeah, we have basically seen this in pictures on Ralph's slides before. There are classical planning problems in public transport, and they are organized in an hierarchical way like this. So in the beginning, there's network design, then there's line planning, so what's happened in Karlsruhe. If you know what the lines are and what their frequencies are, you can proceed to timetabling. That means to give arrival times and departure times to trips. And then basically the strategic planning ends. You go to operational planning, aka how to organize efficient operations from the viewpoint of a public transport company. Then you need to group the trips together to vehicle schedules. And if you have scheduled vehicles, you would be interested in scheduling the crew. First of all, you typically do some abstract combination of duties, and then you assign the duties to the crew. That depends a little on the context. And in the end, there's real-time management. And that is basically things that need to happen on short notice. Network design is something that might take decades to build a new railway line, for example, a new railway tunnel. Real-time management must somehow be in real time. Network design, again, is something that involves many decision makers because it's a highly political question. It costs a lot of money. And in the worst case, real-time management is just one single person sitting at the disposition center and needing to solve all these problems in a row in a few seconds or minutes. This is basically the things, and that is organized, as you can see, in this order, but you might actually notice that the best way would be to solve everything all at once, right? Because if you have a bad line plan, it might be that your timetable is even worse and the vehicle schedule is not better. And these are points when you would like to go back and say, well, if I change this line a little bit, or if I change this departure here a little bit, wouldn't I get a much better vehicle schedule or cruise schedule, right? And that's why you occasionally need to go back. But still, that makes the problems, of course, more complex the more steps you integrate. I will be talking about periodic timetable optimization, which is, of course, part of timetabling here. Yes, what is timetable optimization? Informal definition would be, and a timetable is an assignment of arrival and departure times to a given set of trips. So it does not involve the choice of lines and also not the choice of service frequencies. That's already fixed. You know, you have this line, it operates every 10 minutes, but at what time exactly? That is the question. And there are two things for timetable to be noted. One thing is that the timetable should in some sense be valid. So you want to associate realistic travel times, right? So there are some physical constraints on driving between two stops or two stations that should somehow be reflected in the timetable. There might also be some constraints on minimum transfer times. If you need to go from platform 1 to platform 27, that might take a few minutes. You cannot just do that arbitrarily. And what is particularly important in the context of railways is the so-called conflict freeness. That means the timetable needs to be planned in such a way that trains do not crash into each other. That is also reasonable, but for example, it does not play a role on the planning level for trams. For example, for trams, you'd always say they drive on site, they will just figure out what to do in such a situation, right? But for trains, it's necessary to guarantee a sufficient headway time between two trains. But also conflict freeness is important, let's say, for bus timetables, if you have electric buses or other buses, and you need to line them up at the terminal station. And if this terminal station has just limited capacities, well, you cannot just do arbitrary arrival and departure times there. You need to respect the capacities of parking spots, let's say. Right, so this is what needs to be guaranteed on the planning level. The next question would be, what makes a good timetable? And I actually would like to give this question to you. So what do you think makes a good timetable? And what does it mean precisely? Minimize travel time. Okay, that's okay. One more. Okay, there was also William. What? So, easy to remember, great. No, it's in fact an important point. It's I think the main reason for periodic timetables, right? Sorry. Reliability. Okay, that goes onto the direction of robustness, more or less, right? So, okay, yeah, very good. Funny to notice, I asked this question also to people that study traffic engineering, and all of them said you must have efficient resource usage, which you didn't say at all, right? Because they think in terms of public transport companies, and what they think of a timetable is, well, I should need as little vehicles as possible or as little drivers as possible, right? He didn't say that at all, but all of them said that, and they didn't think at all about short travel times, which I found really surprising. So you see there are many perspectives on this. There's a passenger perspective that will tell you, well, I don't want to wait hours until my trip actually departs, and when I'm in the vehicle, I want to have short travel times, and when I transfer, I want to have short transfer times. Of course, in the reasonable timetable, the driving times, there's not so much you can do about those, but transfers, right? This is something you can really optimize. Then there's the operator's perspective, which is about vehicles and drivers. And the reason behind that is, at least how public transport is typically organized in Europe, public transport companies do not get any reward for offering short travel or short transfer times. It's just not part of part of their contracts or part of their objectives, because they're not paid for that, right? There might be some indirect effects, like you get more users if you offer passenger-friendly timetables, but typically they need to get money from the state to pay the vehicles and to pay the drivers, and that's basically what they care for most, right? So this will be their main focus. Then there's, again, the railway perspective, and we have the system in Europe that there's a difference between companies that actually operate the railways, so these are the companies that own the trains, and companies that own the network. And timetables, in that sense, are requested by the operators, but constructed by the infrastructure managers. And what they want to do is they want to sell their tracks to the operators. And their objective is basically to use as much of the track capacity as there is, to sell as many track capacities as they can. Again, a completely different viewpoint. They don't care about passenger transfers. They don't care about the number of vehicles an operator needs. It's just selling the capacity. And there's this position, which is also important to all of them, in fact, is maximize robustness against disruptions and delays, right? So, of course, you don't want to have a timetable where you're always at minimum transfer times on your trip, because as soon as there 1 minute of delay, the whole connection breaks down. And that's bad for passengers, but it's also bad for operators, because if the vehicles get messed up too much by delays, then it's hard to actually get back to normal operations again. And what you might have seen here is that these goals, they are partially conflicting, right? So you cannot offer something that satisfies everything, right? It might be that a timetable that offers short turnaround times at the endpoints, which is good for the number of vehicles you need, is not one that offers short transfer times, right? So this is a balance, again, you need to make. And the most difficult problem is, again, this balance between passenger perspective and operator perspective, as it's already for line planning. Sorry? Thanks. Great. Let's start speaking about how we as mathematicians actually think about those things. So the starting point would be a line network like this. I think I do not need to explain you what this actually means. You have seen these objects, but for the sake of exposition, I will start with a smaller one. Let's say this. It has the same meaning, right? So there are stations, there are lines, great. And what we do now is to distinguish arrivals and departures, we blow this network up. And then it looks like this. So basically what we have done is we have added directions, forward and backward direction, you could say, like here. So this is going from this station to that one. This one is back. This is a turnaround at the station. This is a dwelling at the station. So the vehicle stops in the station between arrival and departure. And these grayish arcs are possible transfer relations for passengers. And they always go from arrival to departure. So it's just it's a very abstract construction that we're just making. And we call these vertices here events, arrival events, departure events. And the arcs are activities. They are driving, dwelling, turning, transfer. You could also think of more things, whatever you like. For example, you could separate two lines by a certain headway, for example, and so on, but I won't do that here. And to make this into a proper instance of a timetabling problem, we associate to each of these arcs bounds. And bounds could be driving times, minimum times for transfer, maximum times for dwelling at the station, and so on. And also weights. And weights could be the number of passengers that we think are using a certain activity or a certain transfer. But we could also, to get more to the operator's perspective, say we just penalize turnaround times here, because if the vehicle is at the terminal station, it waits for the next departure, there's no passenger involved. Passengers don't care about that, but the operators care very much, because the more time you spend here, the more vehicles you need, right? So you could penalize this. And finally, since we are talking about periodic timetabling, there's a period time, we call it capital T, that could, for example, be 60 if I want to capture a resolution of 1 minute for 1 hour. And then we have the input for the so-called periodic event scheduling problem, which is called PESP. So we're given such a directed graph, which is called event activity network. We're given a period time, lower bounds, upper bounds, and weights on these activities. And we want to find a periodic timetable pi and a periodic tangent x. the periodic timetable pi is just an assignment of times to the vertices, so an assignment of arrival times and departure times. And because the timetable is periodic, it makes sense to choose them between 0 and the period time t, because the timetable is supposed to repeat after the time t. So we can just say we pick a representative between 0 and t. And periodic tension is supposed to model the activity durations. And there's a connection between departure times, arrival times, and activity durations, namely the following. That if you look at a specific arc in the graph and you look at the time points at the endpoints and take the difference, then that should equal the duration. But since we are again periodic, we only want to be this congruent to this duration modulo the period time. So an example for this, let's suppose we have a period time of 10 minutes. And then there's a, let's say, departure at time 6 and then arrival at time 9. The difference is 9 minus 6, which is 3. And that could be a duration of 3. But in a periodic timetable, it doesn't matter if the duration is 3 or 13 or 23 or 33. It just doesn't matter because the timestamps won't change, right? And that's why we have this modulo t here. Or likewise, if we have an arrival at, let's say, 5 and the departure at 9, the difference would be minus 4. But that is not a valid duration for anything that happens in the world, right? So we don't take minus 4, but 6 or 16 or 26, right? This is why this modulo is there. And finally, we of course want that these activity durations, they adhere to the bounds, and we are optimizing, so we want to minimize the total weighted periodic tension. So if the weights reflect passenger loads, this just means we want to minimize the total travel time of all passengers, plainly as it is. And yeah, so that is the problem. It might, of course, be that something like this does not exist, so it's not automatically feasible. So that will be also part of the problem to decide that. And as you see, there are some inputs, but there are not so many constraints, and it's completely straightforward to formulate this as a mixed integer program. So you minimize this weighted tension here. You have the bounds for x and for pi. And the only thing you need to think about is how to resolve this modulo t constraint. And you do this by adding artificial integer variables, because that says pi j minus pi I and xij differ by an integer multiple of the period time. And this integer multiple is the variable you add here and require it to be integer. They're called periodic offsets. And this is a little bit cheating, because if you look at this, this is not what you typically can do in a MIP. So you would replace that by a less than equal t minus epsilon for them, some epsilon, for example. In many cases, this epsilon is just 1. And what you could also do is, because this x is always supposed to be at least the lower bound, you could subtract x from your lower bound, and then you get an object that's called periodic slack. So the extra time you spend on top of the lower bound, you could also minimize that. It just differs by the constant term. So that's the model. To give an example, that would be a small event activity network. We have 2 lines, a red one and a blue one. They meet at the common station in the middle, and the dotted arcs are turnarounds and the dashed arcs are transfers. And you see lower bounds, upper bounds, and weights. Yeah. Now I'll give you the task to optimize. Let's try this first by hand. And in fact, because of all these modulo constraints, that is harder than you might think. So let me give you my lines of thoughts on this. So first observation is, if timetable and tension are optimal, then you can compute this tension as the difference of the timings modulo the period time, but it's not quite true. You need to catch the right representative, which is between the lower bound and the upper bound, and then the first one, the smallest one. And this is the complicated formula to express this. So modulo 10, it's just pi j minus pi a, but this number is supposed to be the modulo. It's between 0 and 9 or 0 and 10. And this guarantees that this is at least the lower bound. Okay, that already looks a little bit stupid, but that is certainly true. And then you notice some activities here that are actually fixed. So lower bound equals upper bound. So you immediately know what the right value for the duration is. So you can just fix them. And if you fix that tangent here to 7, you know that these 2 time points just differ by 7. Right, so pi b will be pi a plus 7 modulo 10. Okay, and if you actually now assign random timings to, let's say, the points at A, C, E, and G, you will see that this can do this at first. Whatever you do is fine if it's integer, because there are no restrictions on these durations here modulo modulo 10, so any integer value of this tangent would be fine. The bounds do not restrict anything. And of course, if you restrict A, C, E, and G to something, then you automatically know what B, D, F, and H are. Okay, so this is the objective value. These are all the terms. These are the weighted tangents, and I just dropped the ones where we just had 0 weights, and then you see the lower bounds arranged here. And then you can rearrange this a little bit, plug in values, and now you group these summands here a little bit together. So one thing would be you could group those two, so this one and this one, and you see that this expression modulo 10 is the same as -2, but it's between 0 and 20, but it needs, if it's -2 and between 0 and 20, it must be 8 or 18. There are no other choices. Also, these two add up to 0 modulo 10, but it's again between 0 and 20, so it can only be 0 and 10. And this is something you don't know anything about. It's just that, it's something, right? So the best thing you could actually get is to take all these things at the lowest possible value, 8, 0, 0, and then add this constant term that comes from the lower bound. So 28 would, in my opinion, be the best thing that you can do. And in fact, you can find an assignment that does it, which is assigning those times to A, C, E, and G. Here it is again. And you now can just check. We have 0 here, 7 more, 2 more to 9. And if you go from here to here, it's 5 at the lower bound, but you need to add a slack of 4 to get actually to the 6 that's required here. So at some points, you need this slack to make everything work. And of course, that's not the way you're supposed to solve it in general. You solve it in general. To do it in a less painful way, you have, I think, seen all the basics for that. You formulate a mixed integer program, and it's just like this. And you see it's not hard to write down. So you have the objective function, and you have these timetabling constraints, the bounds, and declare the integer variables. You write it maybe into an LP file format. Then you invoke your favorite MIP solver, and it will solve this thing instantly, and will tell you the value 28, right? And of course, this is the preferred way to solve it. Maybe for time reasons, I will skip this a little bit, that we catch up with the schedule. Complexity. Even deciding whether a feasible timetable exists is an NP-complete question, and this is also true if you fix the period time to a specific value, right? So the question, is there a feasible timetable with a period time of 3 for that network with those bounds, is NP-complete. There's a nice reduction from the coloring problem, which I will just skip for now. And you can even do more. So what would be an easy case? So when can you solve this problem in a straightforward way? And this is the one where the graph that you consider is a tree. And if you have a tree, then taking lower bounds will always work. And you can construct the timetable from that by just traversing the tree, let's say by depth first search. Just let me show you how this works. So you start at the first vertex, give it time 0. Well, then you do depth first search to get to the next vertex, give it the time of 0 plus lower bound, which is 7, then you proceed and so on. And then, well, you go to the second branch and depth first search and do this, and will just work out. There's no problem that could ever occur with this method. Okay, so if trees are easy, then the problem seems to be cycles. There's also another complexity result that generalizes to tree width. I don't know if you have heard of that notion. Tree width is just a parameter that kind of captures the tree-likeness of a graph. And trees have tree width 1. And as soon as you have a cycle in a graph, the tree width is at least 2. If it turns out that PESP is already NP-hard if the tree width is 2. And that also implies that it's NP-hard on planar graphs, for example. And there's a dynamic program and so on. So there's lots that can be told about complexity, but it's just to show you that it's a very complex problem. The trees are easy, but everything else is difficult. So cycles seem to play a role. So let's ask this question. Suppose we have some vector on the arcs of the graph. And the question is, when does the timetable exist such that this timetabling condition here actually holds? So just given any arbitrary vector, how can I see that? And one observation is the following. If you take a cycle in the graph, let's say this cycle C here, it has the vertices I0 up to IN, where I0 is the same as IN because it's a cycle. And then you sum up the tangents. Suppose you have a feasible solution and you sum up the tangents along the cycle. Well, then you know that you always have to take the differences of the endpoints modulo t, but this is a cycle. So what you will end up with here is a telescoping sum. And what you get out of this is that the periodic tangents along a cycle sum up to 0 modulo the period time, necessarily. That also means that if I have cycles in my graph, I might not always be able to realize the lower bounds as the tangents because I have this condition. Along a cycle, I always need to sum up to 0. So let's do this as in a practical example. So this is a part of the Berlin-S-Bahn network. We have 3 lines. And I highlight a directed cycle here. It's kind of driving from here, transferring, driving, transferring, driving, transferring. Doesn't mean that any passenger would ever do that, but the cycle is just existing in the graph. And we know that this condition must hold for a cycle. So let's suppose the period time is 10 minutes. Then the activity durations along the cycle must add up to some integer multiple of 10. That's what 0 modulo 10 means. Okay, now we suppose each transfer takes 2 minutes. And this is the lower bound that we have. And then we have 3 transfers in the cycle. So these will take 6 minutes. That means if I need to add up to an integer multiple of 10, all the driving must be 4 minutes, 14 minutes, 24 minutes. But this might just not be reality. So in practice, all these driving activities will take around 2 minutes. And this is again 6 for all driving activities, but 6 plus 6. So 6 for driving, 6 for transferring. That would be the lower bounds. Is not a multiple of 10, right? It doesn't work out. So you need to add some supplementary time, some slack at some points, either to transfers or to driving times. But basically, this is the example where you can show people why not always short transfers are in fact possible in practice. It's because of their cycles, and you need that the tangents need to sum up to an integer multiple of the period time. Okay, let's do some math finally. Consider a dialectic graph, then you will have heard of the notion of the incidence matrix that just keeps track of how the vertices are incident to the edges. And as any matrix, that is, comes with a linear map. And in fact, it looks like this. So we have some vector on the arcs, and then we'll just give you this, what you know from network flow theory as flow balance at the vertex. And the kernel of that has a name. It's the cycle space. We work over the integers here, so it's not a vector space. It's an abelian group. And this is just by this very definition here, the space of all circulations in the graph. That means integral flows where flow conservation holds everywhere, right? And a cycle is a particular case of a circulation in the graph. And this is an abelian group. It's a free abelian group, and it has a rank, and the rank is just the same as the dimension if I would have done this over a field. And this is called the cyclomatic number. And then there are types of cycles. So we have the cycle space, but this is just integral circulations. We have consider now oriented cycles. These are circulations where we restrict the entries to -1, 0, or 1. Directed cycles are the same as before, but we only have 0 or 1. And undirected cycles are the ones if you forget everything about numbers and just say we have an entry or we don't have an entry. So let's say we work over F2 instead. A finite field with 2 elements. And an oriented cycle is something where you have arcs that can go into different directions. So we have this one entry, it's kind of going in a forward direction, and the -1 goes into a backward direction, like this one here, right? So this would be an oriented cycle. It's not a directed cycle, but it's still some kind of cyclish thing, and we call it oriented cycle. And we now just see it as vectors on the set of arcs, and then by this we can just use vector addition and add 2 of these vectors together. This will also be no longer an oriented cycle, but still a circulation in the graph. And if you do this modulo 2, for example, then you have this undirected cycle, and you can add them together, and 2 goes to 0. So what you've done is symmetric difference of those cycles. This is the typical way you typically introduce the cycle space for undirected graphs. So there's a lot to say about cycles, but why are they important? We will first of all need fundamental cycle bases. And this is something that is, just that gives a basis for the cycle space, and they work like this. You consider a spanning tree of your graph, like this. And then if you choose one of the arcs that have not been blue, like this one, for example, you always create a cycle, right? And if you do that, you get the so-called fundamental cycles. And if you do this for all, you in fact get a basis for the cycle space or the integers. And that also means that you can calculate the cyclomatic number, because you can calculate, why is this empty? let's calculate the number of arcs that are not in a spanning tree, because a spanning tree will always have number of nodes minus 1 arcs, and you just subtract that for the number of arcs in total, and this will give you the number of the cyclomatic number. Don't prove anything here. And in this example we could look at those cycles, which would be the fundamental cycle basis for the spanning tree I just showed you. And what you can then do is you could put those incidence vectors of these oriented cycles into a matrix. So there would be 3 cycles, and then you just put them as rows into a matrix like this. So that's straightforward. That means gamma 1 is a cycle that uses HA, AB, BG, and EF, right? All forward. Gamma 2 is something that uses also things in backward directions. That's why I put a -1 there. And this way you can get such a matrix. We call it a cycle matrix. Now there are different kinds of cycle bases. We will focus on the integral cycle basis, which just means that we have a basis of the cycle space that is the basis of this object in terms of being a basis of the free abelian group in the algebraic sense. That is a little bit different from fundamental cycle base. Fundamental means there is a spanning tree. Integral means that's just some basis. And there's also undirected that actually works over the undirected graph, let's say. And there's an implication that tells you that any fundamental cycle base is in fact integral and any integral is undirected, but the reverse implications do not hold in general. In fact, there's a whole theory of cycle basis graphs of different types, and there are difficult implications between them. But we will stick to the cycle matrix I've shown you before. Let's not do this. And because they're important for something. And that now brings us back to timetabling. So if I have a vector x over the set of arcs, then the following are equivalent. The first thing, there's actually a pi such that x is xij is pi j minus pi I for all arcs modulo t. So that's the thing we need for timetabling. The second condition is if I sum up the tangents along an oriented cycle, then the outcome is 0 modulo t. You've seen this for directed cycles with the telescoping sum. It's also true for oriented cycles, but you need to be careful about tracking the signs of forward and backward arcs. And the third thing is that if you take the cycle matrix that I showed you, so you take a basis, write the oriented cycles as rows, then the same thing holds. This cycle matrix gamma times x is 0 modulo t. And this is, for this you need the notion of an integral cycle basis. And there's an algebraic proof of this that relates to graph homology, if you like that, if you've ever heard of that. There's also an easy proof of this, because for going from 1 to 2 is the telescoping sum. Going from 2 to 3 is just noticing that the rows of the cycle matrix gamma are composed of oriented cycles. Going from 3 to 2 is just using the fact that each oriented cycle is an integral linear combination of the basis vectors, which are the rows of that matrix. So that is fine. And from 2 to 1 is again the thing, if I do my depth first search, I construct a spanning tree. Along the spanning tree, I can just construct a timetable as if the graph would be a tree. Then this is fine for all the arcs on the tree. And the only thing that could go wrong is at the arcs that are not part of the tree. But then I just check that I can define my tangent in such a way that everything works out. Yes. And with this characterization, we can do something. We can get a different MIP formulation. Namely, instead of saying we need pi j minus pi I equals xij modulo t, we just can say, well, gamma transpose x needs to be 0 modulo t, and 0 modulo t is again modeled by introducing a vector of integer variables, which is called z here, and then this is the formulation now in vector notation. And you see the timetable pi is gone. It's not necessary, in fact, to understand the nature of timetabling, which is interesting, but you can reconstruct it again with the step first search procedure. And the thing is, the formulation we had before that had as many integral variables as there were arcs, this one has only as many as their linear independent cycles, and this is less. That's why this is important. The downside is that the range of those variables here might be larger. So it's kind of a trade-off, but it's a different formulation. And again, you can write down this formulation. It's not easy. It's not hard to understand. So you have these 3 cycles here that give you 3 constraints. So along these cycles, the tangents need to up to an integer multiple of 10. You have to do this for 3 cycles. You write down the bounds. That's it. And again, you can use your favorite MIP solver to solve this. Great. What is now the downside of this? So I basically told you now, used one of those 2 MIP formulations, solve it. The problem is that it's not that easy for real-sized instances. And one reason is for this, that the LP relaxation is just complete bullshit because it can always stay at lower bounds. And one way to see this is the following. If you drop the integrality, you set the timetable to 0, this to lower bounds, and you take this integer multiple of your period time to just some very fractional thing, namely lower bounds divided by t. Same for the cycle-based formulation, and this always works. So the LP relaxation doesn't give you any information that you would like to have, right? It ignores everything. So this is not good for branch and cut, in fact. So what's behind MIP solvers? And for this, it would be wise to think at least about cutting planes. And the easiest class of cutting planes are the so-called cycle inequalities. And they just make use of the fact that along a cycle, the tangents need to up to an integer multiple of the period time. And for this, you just look at such an object. It's the sum of tangents along a cycle divided by the period time. It needs to be an integer. And then there are obvious bounds for this. So you take the upper bounds for all arcs that are forward and subtract the lower bounds for all arcs that are backward divided by t and round it down. It's so straightforward to see that this works. It's the same thing as Gomori-Schwartal cuts, if you have heard of them. And you could add those. Interesting. And you can also use those to put bounds on these cycle offset variables z, so these artificial variables, because they also just belong to cycles. Yeah, how does this work? So again, it's a similar shaped instance. The numbers have not been worked out by myself, but so if you saw that, you see in blue here now the value of x, so the tangent, which is now the LP relaxation values, and we'll put everything to the lower bound. That means you add nothing on top of the lower bound, so the weighted slack will be 0. Now let's consider one cycle. You add this cycle inequality, and it will tell you that the tangents need to add up to at least 10 along the cycle, but it has not been true before, so you need to change that 1 that was here before to a 3 to make this work. And this is what will come out of your solver. Yeah, and this is basically the way this works. Then you would ask for the next cycle, add again this inequality, and by this, at some points, the numbers will go higher at some places. And then finally, if you have added all cycles that you can potentially see here, in effect, the LP relaxation with these extra inequalities will give you the right value in the end. Right, so it's basically a simple example where a pure cutting plane approach brings you to the MIP solution at the end. It's not always that easy, but in this example it is. Yes. Final remarks. I want to emphasize that the problem I presented to you so nicely looks quite innocent, but it's computationally very hard. So medium-sized instances can be very challenging, but still these models are applied in practice. So, for example, this timetable-based formulation, the first one I showed you, is good for finding feasible solutions. The other one is better towards optimality, right? So you can prove optimality faster and get better dual bounds. There's more to discover. So there's a rich combinatorics of optimal solutions. They're again related to spanning trees. There's a network simplex type algorithm that serves as a heuristic, which is quite nice. There's also an interesting geometric picture to this. It has to do with things like tropical geometry and also with zonotopes. So we also developed a heuristic for that. And of course, this is a very basic model for timetabling purposes. There are many aspects in public transport that you would like to cover as well. And there's also a lot of research on combining this PESP model that I showed you with other techniques like line planning, for example, that you've seen before, but also things that are more railway applied, like track allocation and track occupation conflicts and vehicle scheduling. Yes, finally, we have something developed here at our institute, which is a solver for these type of problems, and it has a lot of things that I haven't had the chance to talk about, but there are many ways to approach this problem. We have a solver that integrates all these techniques in a concurrent way, and it actually turns out to be the best code that exists for these instances in the world. And we hold basically all records for benchmarking library that is around. And finally, if you want to try it yourself, it's unfortunately in German, but you will understand. We have a very small JavaScript game where you can actually try to optimize the timetable for this network. So you need to enter the times into the node labels, but it need to be consistent with the bounds and so on. And the goal is basically to minimize the travel time of the passengers. So if you want to try it yourselves, you're welcome to do that. I will stop here and I'm looking forward to questions.